Okay, you guys have some homework. So what I want to do is give you sort of a sample problem that'll give you an idea how vectors, how like hat vectors and things get used. So we're going to say here is a star, and it's yellow, of course, like most stars. Well, not most stars, but like some stars, and it's bright and happy. And its mass, hold on, let's use capital M for that, is let's just say 2 times 10 to the 30 kilograms. And flying along, fairly close to the star is, of course, nothing other than the Millennium Falcon, which is Han Solo's spaceship from the Star Wars movies. If you don't remember this, just remember that, just remember it's a spaceship. And trust me, it looks like this. I mean, sort of. Okay, so let's say the Millennium Falcon's, or the position of the star. So the Millennium Falcon sees the star, or Han Solo and Chewbacca. See the star. That was my Chewbacca noise. And the position of the star, with respect to them, is let's say I don't know. Let's say it's like 4 I hat plus I don't know, 6 J hat. No, actually, you know what? I'm going to do 4. I'm going to cheat and make it sort of easy. 3 I hat plus 4 J hat times 10 to the 6th, or sorry, not plus, times 10 to the 6 kilometers. That's its position relative to them. Okay? And the mass of the Millennium Falcon, which is little m, is going to be, I don't know. Let's see, how heavy would that be? 1,000 kilograms a ton. So let's say the Millennium Falcon weighs like, I think it's a big, it's a freighter, right? So let's say it's 20 times 10 to the 3rd kilograms. So that's about a 20-ton spaceship. I don't know. That seems, no, that's light. That's like 10 SUVs. It's bigger than that. So let's say it's 200 times 10 to the 3rd kilograms. Okay, great. Or we can call that 2 times 10 to the 5th kilograms. Whatever. Okay, and we want to find the force, the vector force that this star here, that the Millennium Falcon is flying close to, exerts on it. So force. Let's take our equation for gravitational force. Now the magnitude, remember, is capital G, big M, little m, over r squared. Easy enough, right? Now, the official definition, the sort of the official version of the formula is negative that magnitude times r hat. But what's important here is to think about, whenever you're doing a problem like this, think about which way the gravity should be going and adjust the formula if necessary. Don't be a slave to this minus sign if you know better. So, and this is a case where you need to know better. So, which way is the sun's gravity going to, pull or push the Millennium Falcon? It's going to pull it towards the sun, right? Okay. So, there's your force. Now, is that in the negative r hat direction or the positive r hat direction? Remember, this in here, this stuff that I am putting the orange, box around, that's all magnitude stuff. Direction, all that matters is the negative sign or lack of a negative sign and the hat vector. Okay, so which way does r hat go? R hat goes this way, right? This little blue vector there that I've just drawn is r hat, or it's the direction of r hat. It's a magnitude 1 vector that goes in the same direction as r. So is it correct to say that the force is going to go negative of r hat direction? No, it's not actually. It's going to go in the same direction as r hat. So in this case, we need to squeak out the r. Squeak out the negative and just keep the r hat. Now, the reason why it's done negative is because they're sort of assuming the convention would be, say you have an object here. Say this is M1 and here's M2, and this r vector goes from M1 to M2. Then, if you were looking at the force on M2 from M1, then this force is going to equal negative G big M little m over r squared times r hat. okay? Because in this case, the force is going the opposite of the way you got your r vector going. In fact, you can call this like F2, the force on 2, right? But if you were trying to calculate the force on 1, then what you'd have is that F1 equals positive, that's a plus sign, G M1, M2. I'm sorry, this should be, maybe this will make it a little more clear. This should be M1, M2. M1, M2. And this should be positive G M1, M2 over R squared times R hat. So you can see how the convention is, if you're going from 1 to 2, then the negative sign, you know, is what you put in if you're calculating the force exerted on 2 by 1. But in this case, we're looking at the force exerted on the Sun by the Millenium Falcon. Or sorry, if that's exactly the opposite, actually. What we're looking for is the force exerted by the Sun on the Millenium Falcon. Did I say? I don't even know what I said now. Oh my God. Okay. But we have a vector going from the Millenium Falcon to the Sun, not vice versa. So that's why we take the negative sign out. So the important thing is always look at your problem, figure out which way, you know, your r vector is going and which way gravity should be going, and adjust the positive or negative sign accordingly. Don't just blindly, you know, do it one way because the negative sign is there. Okay, so now that we've settled that, we want to actually evaluate this. So actually, let me get rid of all this crap down here because that's just going to take up space. Right, so there we go. Okay, so let's look at what this is going to be. F equals, so G, which is 6.67 times 10 to the negative 11. We're going to do everything in newtons, meters, and kilograms. So if stuff doesn't come in one of these, we're going to have to convert it, okay? So there's our capital G, like that, okay. Now our, oh, you know what? Okay, so I should have, before we plug in numbers, I want to say this is not the most convenient way to use this because we would have to calculate the r hat vector to use this formula. So what we're going to do instead is we are going to take an identity, which is r hat is the r vector divided by the magnitude r, plug that in, and then what happens is that this becomes capital G, big M, little m over r cubed times the r vector. Okay, so that just saves us the step of having to explicitly calculate this, as it just sort of builds it in. Okay, so now we're taking this equation here and implementing that. So this is the mass of the Sun. So this is 2 times 10 to the 30 kilograms. And then the mass of the Millennium Falcon, which is 2 times 10 to the 5 kilograms. All of that over r cubed. And hold on a second, Mr. Rose is at the door. Hello. Okay, that was just Mr. Rose. He had a question for me, but it's all settled now. So I told him that aardvarks don't eat peanuts, so he was wondering about that. Okay, so now we have to take this, you know, the magnitude of r, which we actually haven't calculated, so I better calculate that. So the magnitude of r is, well, you take the magnitude of this times the 10 to the 6 kilometers. So the magnitude of r is, I'm going to cheat and say I know the magnitude of this is going to be 5 times 10 to the 6 kilometers. And you could see that if you did square root of 3 squared plus 4 squared would be then 25, and square root of that is 5 times 10 to the 6 kilometers. So r cubed, now this is our scalar, you know, our magnitude of r. This is in kilometers though, and we need this to be in meters, right? So it's actually 5 times 10 to the 9th meters cubed, right? 10 to the 9th meters cubed, and that's all cubed, okay? And then times our r vector, which is 3 I hat plus 4 j hat times 10 to the 6 kilometers, but it's actually, again, 10 to the 9th meters, or I'm going to leave the meters off. Okay, now, here's where I think it's important and it's helpful to handle all your powers of 10 first. So what I want to do, we've got a case here where powers of 10 is cubed. So what I want to do, instead of doing 5 times 10 to the 9th and cube it all, what I want to do is simply cube the 5 Let me see if I can draw that a little better. There's and then 10 to the 9th cubed is 10 to the 27th. Okay, so now I'm going to add up my powers of 10. I've got so I'm just going to do that. I'll do that in orange over here at the end. So I've got negative 11 from here. I've got 30 plus 30 plus 5, and then down the bottom I have negative 27 because it's 27 on the bottom, and then plus 9 at the end here. So negative 11 plus 9. Okay, so negative 11 and 30 is positive 19, plus 5 is 24, and then we subtract 27, so we get down to negative 3, and then we get plus 9, so we get equals positive 6. So what I'm going to do then now is, to make this a little easier then, we can just do F equals 6.67, okay, times 2 times 2, 2 over 5 to the 3rd, times 3i hat plus 4j hat, and then this is all everything times 10 to the 6th newtons. Okay, so just doing our little power calculator here. Let's see, so the x component, we're going to have our 6.67 times 2 divided by 5 to the 3rd. Okay, and then for our x component, we'll multiply that by 3. And what we get is that, so 6.4032 times 10 to the 5th newtons. So I think what's going to happen is I'm just going to mentally put in a, so 6.40 I hat, and we have to remember that we're taking 1 away. Okay, so and then the other one is going to be times 4, and that is going to equal 8.54 if we round, plus 8.54 j hat times 10 to the 5th newtons. So that's going to be the force on the Millennium Falcon. And if you want to find its acceleration, you would just take all this and divide this by 2 times 10 to the 5th kilograms, and you'd get the the acceleration of the Millennium Falcon. But there's our answer, and so that should hopefully help you understand what we're doing with some of these WebAssign problems and how to handle vectors. And the important thing I would say is always check the direction of your forces. Be careful. Think about it. Think about which way a force should be going on a certain object, because your R is always gonna be, you're not always going to be given R going from one to the other, and it's going to sometimes be convenient to do it this way, and then you have to remember to take the negative sign off. So the important thing is just to check, use your intuition, trust that. Don't let the equations force you to do something that doesn't feel right. Okay, anyway, that's all.